Welcome to Inorganic Chemistry. Today, we are diving into the fascinating world of valence bond theory. If you have ever wondered exactly how two separate atoms lock together to form a stable molecule, you are in the right place. We will build this understanding from the ground up, step by step. Let us start by imagining two people walking toward each other to shake hands. When far apart, they do not interact. But at the perfect distance, their hands overlap to create a stable connection. Valence bond theory is exactly like this handshake, but for atoms. It tells us that a chemical bond forms when the outer electron clouds or atomic orbitals of two atoms physically overlap in space. The electrons in these half-filled orbitals pair up, spinning in opposite directions. This shared space creates a powerful negative charge density that acts like a glue, pulling the two positively charged nuclei together. Now that we understand the physical picture, let us look at the mathematics behind it, known as the Heitler-London approach. Imagine two completely separate hydrogen atoms. We will call them atom A and atom B. Atom A has an electron named 1, and atom B has an electron named 2. In quantum mechanics, the behavior and location of these electrons are described by a mathematical function called a wave function, represented by the Greek letter psi. When the atoms are far apart, they do not affect each other at all. This brings us to our first mathematical equation. Because the two atoms are completely independent when they are far apart, probability rules tell us to simply multiply their individual states together. Here, psi s represents the total mathematical description of the two separated atoms. Psi a of 1 is the state of the first electron on atom A, and psi b of 2 is the state of the second electron on atom B. If the distance between the atoms decreases, they begin to interact physically, which means this simple multiplied equation will need to evolve to describe the new shared system. So what exactly happens as these atoms get closer and their orbitals begin to overlap? A strange and fascinating rule of quantum mechanics takes over. Electrons are completely identical and indistinguishable from one another. We cannot paint a tiny number on them to tell them apart. Therefore, once they share the same space, it is equally possible that electron 2 is now orbiting atom A and electron 1 is orbiting atom B. We must write a new wave function called psi x to represent this exchanged scenario. Both the original state and this exchanged state are equally likely to happen in reality, setting us up for the next step. Because both the original and exchange scenarios are equally probable, the true description of the covalent bond must include both possibilities at the exact same time. We combine them by simply adding the two equations together. In quantum mechanics, adding these probabilities mathematically lowers the overall energy of the system, which is exactly what makes the chemical bond stable in the real world. This gives us our final result, psi c, the pure covalent wave function. This equation perfectly describes the equal sharing of the two electrons between the two positively charged nuclei, locking them into a stable molecule. The pure covalent equation we just derived is brilliant, but it has a major flaw. When scientists measured the actual energy required to break a bond, they found the real bond was much stronger than our equation predicted. Linus Pauling realized why. The pure covalent equation assumes electrons are always perfectly shared, but electrons are constantly moving. Sometimes, just by random chance, both electrons might temporarily end up sitting on the same atom. This creates a temporary ionic state, where atoms are held together by the attraction of opposite electrical charges. To account for these temporary charged states, Linus Pauling wrote a new equation. Here, psi I represents the total ionic contribution to the chemical bond. The first term describes the situation where both electron 1 and electron 2 are sitting on atom A, making it a negative ion. The second term describes the exact opposite situation, where both electrons are sitting on atom B. Even in a perfectly shared bond like hydrogen gas, these ionic states exist for tiny fractions of a second. When the probability of these states increases, they add an extra attractive force that strengthens the bond. To get the most accurate picture, Pauling combined the pure covalent wave function with the new ionic wave function. This is Pauling's improved wave function, psi t. He introduced a mixing coefficient, represented by the Greek letter lambda. Lambda is simply a fraction that controls how much ionic character is added to the mix. If lambda is very small, the bond is almost entirely covalent. If lambda is larger, the bond has a lot of ionic character, making it much stronger than pure sharing alone. Let us look at this visually. This diagram shows the potential energy of the hydrogen molecule as the atoms get closer. The dashed curve represents the pure covalent sharing model. Notice it only dips down slightly, meaning the predicted bond is relatively weak. The solid curve represents the true bond with Pauling's ionic covalent resonance. It dips much deeper into negative energy. This deeper well means the atoms are held together much more tightly, requiring significantly more energy to pull them apart. The difference between these two minimums is the resonance energy. How do we translate this mixing coefficient into physical reality? In quantum mechanics, the probability of a state is proportional to the square of its coefficient. The covalent part has an invisible coefficient of 1, so its weight is 1 squared, which is 1. For the ionic part, we calculate its statistical weight, Wi, by squaring the mixing coefficient, lambda. Once we have the ionic weight, we add it to the covalent weight of 1 to get the total weight. Finally, dividing the ionic weight by the total weight gives us the percentage of ionic character. Let us see this with a concrete example. Suppose a chemist determines that the mixing coefficient lambda for a bond is 0.25. We want to find the percentage of ionic character. First, we square lambda to find the ionic weight. 0.25 squared gives us an ionic weight of 0.0625. Next, we need the total weight of all parts of the bond combined. We add the pure covalent base weight of 1 to our ionic weight, giving a total weight of 1.0625. Now that we have both weights, we can find the final percentage. We take the ionic weight of 0.0625 and divide it by the total weight of 1.0625. Then we multiply by 100 to convert the decimal into a percentage. The final answer is 5.88. Physically, this tells us that the bond is approximately 5.88% ionic and about 94% covalent. The electrons spend a small fraction of their time completely shifted to one atom, adding extra strength to the bond. This extra strength from the ionic shift directly affects the energy required to break the bond. The total bond dissociation energy, ET, is simply the sum of two distinct parts. EC is the baseline energy predicted by the pure covalent sharing model. ER is the resonance energy, which is the extra stabilization provided by the ionic covalent mixing. When the resonance energy variable increases, the total bond energy increases significantly. This means the atoms sit in a much deeper energy well and are much harder to pull apart in physical reality. Let us solve a quick problem to see the real impact of Pauling's theory. A pure covalent model predicts a bond dissociation energy of 300 kilojoules per mole. However, the ionic covalent resonance provides an additional stabilization energy of 132 kilojoules per mole. To find the true strength, we simply add the pure covalent energy and the resonance energy together. 300 plus 132 gives a final result of 432 kilojoules per mole. Ignoring resonance would have underestimated the bond strength by over 30%. We have covered a lot of ground today. Remember, chemical bonds form when atomic orbitals overlap, allowing atoms to share paired electrons. While the pure covalent model of equal sharing is a great foundation, it drastically underestimates the true strength of the bond. By adding Pauling's concept of ionic covalent resonance, where electrons temporarily shift to create charged states, we get a mathematically perfect picture. This understanding is crucial as it dictates the exact angles, lengths, and strengths of the molecules that make up everything around us. Great job following along.